All right, today we're going to tackle a big one, thermodynamics. Now, don't let the name scare you. This isn't about a bunch of complicated math. Think of it more like the secret operating system of the entire universe. It's the set of rules that explains everything from why your coffee gets cold to how stars shine. So you ready? Let's get into it. So let's start with something you see every single day. You make a nice hot cup of tea or coffee, you get busy, and you come back to a lukewarm drink, right? It happens every single time. But think about this. Have you ever seen a cold drink on your table just spontaneously start heating up on its own? No way. So what's going on here? Why does energy seem to be a one-way street? That's the big question we're going to answer together. Okay, so to figure out our coffee mystery, we first have to learn to think like a physicist. And the most important first step, it's all about defining exactly what we're looking at. Seriously, being super precise here is the key to everything. Before we can learn the rules of the game, we gotta set up the playing field. First things first, we need to talk about the system. And all that means is, what part of the universe are we paying attention to? For us right now, the system is the hot coffee. That's it. It's the star of our little drama. We're basically drawing an imaginary circle around it and saying, okay, everything that happens inside this circle is what I care about. So, if the coffee is our system, then what about everything else? Well, that's what we call the surroundings. The air, the desk, the room, even you. That's all part of the surroundings. And that line, the thing that separates our system from the surroundings, we call that the boundary. Sometimes it's a real thing, like the walls of the coffee mug. But sometimes it's just an invisible line we imagine for our experiment. Now, this idea of a boundary is really useful because it helps us classify systems into 3 types. Just look at this table. First, you've got an open system. Think of a boiling pot of water. It's letting steam out, that's matter, and it's letting heat out, that's energy, so it exchanges both. Then there's a closed system, like a sealed water bottle. You can't get water out, so no matter is exchanged, but you can feel it get warm or cold, right? So it does exchange energy. And finally, the perfect one, the isolated system. This is like a flawless thermos. Nothing gets in, nothing gets out. No matter, no energy. Getting these 3 types down is going to be super helpful. All right, you with me so far? Good. Because we're about to hit the big aha moment of this whole thing. See, to really get a handle on energy, you have to understand that there are 2 totally different kinds of measurements. There are things that only care about where you end up, the destination, and then there are things that care about the entire journey you took to get there. And this is the perfect analogy. On one side, we have state functions. Think of this like your final altitude when you climb a mountain. Once you're at the top, doesn't matter if you took the super steep direct path or the long scenic route. Nope. Your altitude is your altitude. It only depends on your current state. But on the other side, we have path functions. This is like the actual distance you hiked. Of course, the path matters there. The long route means you walked way more miles. Get the difference? One is the destination, the other is the journey. So what are some examples of these state functions? Well, think about the properties of the system itself. Things like temperature, pressure, and volume. If you have a balloon full of air, I can tell you its pressure and temperature right now. That's its state. I don't need to know how you blew it up or if it was colder before. All that matters is what it is right now. But now, let's look at the path functions. The 2 big ones are heat and work. And this is a huge point, so lean in. A system doesn't have heat inside it. That's not a thing. Heat is the name for energy that's in the process of crossing the boundary. It's energy in transit. It's like you don't contain a certain amount of driving in your car, right? Driving is the action, the process of the journey. Heat and work are exactly like that. They're the story of the journey energy takes. And this leads us to a little myth busting, which is always fun. We always see things like heat is flowing into the room. It makes it sound like water or some kind of invisible substance. But that's not really what's happening. Heat is just the term we use for energy that's on the move because of a temperature difference. The system itself has internal energy, sure, but when that energy crosses the boundary to something colder, we call that process heat. It's a verb, not a noun. Okay, so we've got our vocabulary down. We know about systems, surroundings, and the difference between a journey and a destination. Now we're ready for the main event. We're ready to unpack the actual laws of thermodynamics. These aren't just suggestions. These are the absolute unbreakable rules for every energy transaction in the entire cosmos. So we start with the zeroth law. Yeah, I know, weird name. They came up with it after the first and second, but realized it was more fundamental. Anyway, all it says is this. If object A is the same temperature as object C, and object B is also the same temperature as C, then A and B must be the same temperature as each other. It sounds super obvious, right? But this simple rule is the entire reason thermometers work. The thermometer matches the temperature of your body, so you can read the temperature. Next up, the big one, the first law. You've probably heard this one before. It's the law of conservation of energy. Basically, it's the universe's most important accounting rule. You can't create energy out of nothing, and you can't destroy it. You can only change its form. A battery turns chemical energy into electrical energy. A light bulb turns that electrical energy into light and heat. But the total amount of energy in the universe, it always stays the same. But hold on a second. If the first law is true, if energy is never lost, that leads to a tricky question. Why don't things happen in reverse? Think about mixing cream into your coffee. The energy is all still there, right? So why can't the cream just unmix itself and go back into a neat little swirl? The first law doesn't say it can't, but you and I both know that never, ever happens. This tells us something's missing. There must be another law at play. And that missing piece is the second law. This is the one that's famous for being a little mysterious, but it's actually beautiful. The second law is the rule of direction. It explains why time seems to flow forward. And it does this by introducing a new idea called entropy. The law is simple. For the universe as a whole, entropy is always going up. It's always increasing. That's the one-way street we were looking for. So what on earth is entropy? The classic answer you hear is disorder or chaos. But honestly, that's not the best way to think about it. A much more intuitive way is to think of entropy as a measure of how spread out or dispersed energy is. Nature just has a natural tendency to spread things out. Think about it. Energy that's all concentrated in one tiny spot, that's a very special, specific arrangement. But energy that's spread out over a huge area, there are zillions of ways for that to happen. Entropy is really just a measure of how many possibilities there are, and nature loves possibilities. And just to round things out, there's the third law. This one basically sets the ground floor for entropy. It says that if you could cool something down to absolute zero, that's minus 273.15 Celsius, the coldest anything can possibly get, the entropy of a perfect crystal would be zero. Why? Because all the atoms would be perfectly still in one single arrangement. There are no other possibilities. It gives us a 0 point on the entropy scale to measure everything else against. Okay, we have our system. We have our laws. We have entropy. We have all the pieces of the puzzle. So, let's go back to the beginning and finally figure out, once and for all, why our coffee gets cold. Let's walk through it step by step. 1, we define our system, the hot coffee and the surroundings, the cooler room. Simple. 2, the first law kicks in. The energy from the hot coffee isn't destroyed, right? It's conserved. It moves from the coffee into the air molecules of the room. But 3, the second law tells us why it moves in that direction. The energy is all bunched up, all concentrated in that little cup of coffee. The room, on the other hand, is huge, with countless air molecules. There are just so many more ways for that energy to be spread out among all those molecules than for it to stay crammed in the coffee. So it spreads out. And when it does, the total entropy of our universe, the coffee plus the room, goes up. That's it. It's not magic. It's just the universe playing the odds. So you see, thermodynamics isn't just some boring chapter in a physics textbook about engines. It's about life and the universe and the direction of time itself. This quote here from Dixon just nails it. Every single day, every moment, we're using concentrated energy to live. And in the process, we're spreading that energy out, increasing the entropy of everything around us. It's this constant cosmic trade-off. It really is the ultimate story of how everything changes, all written in the simple language of energy.